Okay, so hello everyone. So welcome to our this week Rogers Efficient AI seminar. And today we have the very glad to have Professor Weidong Cao from the George Washington University to give us this very interesting talk, AI-driven analog circuit design automation. And here's some brief bio of the Professor Cao. And he's currently a tenure-track assistant professor in the George Washington University. Before that, he was a principal engineer with the TSMC Corporate Research. And his research interests focus on applying AI/ML technique and the quantum principles to transform the design and the performance of both conventional and the emerging computer system, and span in the field of the VSI circuit design, computer architecture, EDA, and quantum computing. And his work has been widely published in many high-impact journals and conferences, including the Natural Nanotechnology, ICLEA, ICML, and so on. And Professor Cao is the recipient of the ISLPD Best Paper Award. That's a very prestigious the circuit low power circuits conference, and received multiple Best Paper nomination in the top EDA conference, including the DAC and the DATE. So now let's welcome Professor Cao to give us this very cutting edge analog circuit design, AI-driven analog circuit design automation. Okay, Weidong, it's your turn.
Yes. Thank you. Thank you for the introduction. So I feel very honored to be here to give this online talk at Rogers University AI Efficient Seminar. So today I'm going to share our research advances in harnessing deep learning techniques to address a very important engineering problem, analog circuit design automation. And specifically, I will talk about how we can leverage generative AI to tackle these two design tasks, inverse design and topology discovery. When we're talking about analog circuit design automation, I think the first question you may ask is, what are analog circuits? Most people are familiar with digital ICs, as we are living in a digital information world where the binary signals are represented by this like bits dominate the information processing. However, the physical world actually is analog in nature with all kinds of continuously variable signals. So to bridge the physical world and the cyber domain, we need a type of circuits to sense, amplify, and do conversion on these signals. So analog circuits are such essential electronic components to close this gap. And broadly, without breaking analog ICs into several subgroups, representative analog ICs include like sensor, amplifier, ADC, analog to digital converter, DAC, digital to analog converter, just to name a few here. Therefore, analog ICs complement the functionality of digital ICs, and these two types of ICs together build the various advanced IC systems, which we call system on chips. We have seen lots of SoCs in our daily life, such as this CPU, GPU, like TPU, which are used to train or inference in AI machine learning applications. Mobile chips for wearable electronic devices that monitor your health, psychological, conditions, and millimeter wave chips for wireless communication. And the most recent cryogenic chips used for major quantum computing. So given the widespread use of foundational integrated circuits, you may wonder, how do we develop ICs? So this is addressed by electronic design automation. Electronic design automation of integrated circuits is a suite of software tools, right, to automate the chip design flows. So the slide here shows two typical flows used by modern integrated circuits. One is for digital, and the other one is for analog. While there are differences at some stages in these two flows, in general, each flow starts from specification definition, then transits to this architectural design, and the bottom like circuit level design. And the final, we will do physical design. Here, you may notice the different background colors in these two design flows and may pay attention to this analog IC design flow because it is highlighted by this pink color. So this actually introduced the topic that we wanted to discuss today. Why do we need address analog electronic design automation? Unlike the digital ICs that have following a fully automated design flow, the analog ICs relies on manual design flow. This is because digital ICs is easily formulated as several levels of abstraction, such as this ITL, logic synthesis, and all these stages actually can be automated by using electronic design automation tools. However, analog ICs suffer from this low-level abstraction inherently and are harder to be designed automatically. Until nowadays, analog IC design still rely on manual design flow, which is quite time-consuming and results in high design cost. When we zoom in the analog IC design flow here, we can see that each stage can take a couple of weeks, even for an experienced analog IC designer. And what's worse, if the design fails, we needed to repeat the entire design flow and do a lot of iterations to correct the design. As such, analog design actually becomes a bottleneck in the entire IC ecosystem. Analog ICs shares less than 20% of the global market, but they dominate over 85% non-recurring engineering cost and the development cycle of a system on chip. But they just contributed to less than 5% functionality to the entire SoC. However, the demands of IC productivity, such as from the applications, medical, biomedical devices, AI, and quantum computing, are exponentially growing. This calls for advanced electronic design automation tools for analog ICs that can enable high productivity development. And on the other hand, the performance improvement of analog circuits is increasingly challenged. Conventionally, IC performance can benefit from technology scaling, also known as Moore's law. But we can see here, the trend is slowing down, which means that the continuous performance improvement of ICs, especially for analog ICs, cannot benefit from technology scaling. So developing advanced electronic design automation tools to improve the performance of analog ICs can pave the way to the sustainable development of future technology. Combining these two key momentums, advanced electronic design automation techniques for analog circuits are in an urgent need to improve the productivity and development cost efficiency, as well as to enhance the performance of analog ICs in the post-Moore era. So this talk will present the recent analog design automation techniques developed by my group. Specifically, I will focus on the schematic level design. In this stage, schematic level design, there are basically two major problems. So one is the inverse design, also known as device sizing. For this problem, basically, we will find device parameters to achieve desired performance based on fixed circuit topology. This is a very typical engineering problem. For industries, analog IC designers often transfer a fixed topology from an old semiconductor technology node to a new or to a more advanced technology node by reusing a well-established analog circuit topology. This is a conventional optimization problem. We will show that how AI, especially generative AI, can accelerate this design process or can automate this optimization process. The second one is topology design. Here, basically, we develop useful topologies to enable various functionalities, such as operational amplifier, voltage controller oscillator. So this is the most creative design stage in analog ICs because human experts needed to determine what kind of devices to use and how many devices to use. and how to connect these devices to build these functional well topologies. This is very challenging. We are especially interested in exploring how AI can generate or can discover novel circuit topologies that can even achieve capabilities or performance better than the well-established human designs. So this is also similar to using AI to design protein to generate amino acids that can improve human health. In the past few decades, these two problems have been widely studied by using various methods from early optimization to current Bayesian optimization. And most recently, deep learning methods have shown transformative opportunities to address these two problems beyond the limit of any conventional method. Here, I just do a very brief review on recent advances using deep learning methods to automate these two problems. Since the first work applying reinforcement learning to inverse design in 2020, a wide range of learning-based methods have emerged. My group has been actively engaged in this wave of AI-driven analog design automation since 2020. Achieving several key milestones. We published our first work in DAC 2020, and then since that, we have pioneered explorations into several new research directions, such as variation efficiency-aware inverse design, generative inverse design, symbolic-based topology synthesis, and most recently, graph-based scalable topology synthesis. And from this review, we can see that there's a paradigm shift from reinforcement learning to generative AI. So this actually signals a new wave of generative AI-driven analog electronic design automation. In this talk, I will specifically present our advances on leveraging generative AI techniques to address the schematic level design, which includes two parts, generative AI for inverse design and generative AI for topology discovery. So I just start from the first part. First of all, let's revisit this problem definition. By taking a two-stage operational amplifier as for example, the problem is defined in this way. For this fixed circuit topology here, this one, given design goals, which are circuit specifications, such as gain, bandwidth, phase margin, power consumption, we needed to find the device parameters like this width, length of these PMOS transistors and width length of these NMOS transistors, and the capacitance of capacitor here to meet these design goals by satisfying the constraints. So this is actually a one-to-many mapping problem because given this group of design specifications, we actually have multiple group of device parameters that can satisfy this design goal. So this is a typical non-convex optimization problem. The formal mathematical definition of this problem is shown in this box. Conventionally, this problem is solved manually by human designers with a lot of iterative optimization process, which is quite time-consuming. There have been various methods studied to address this problem. Conventional optimization-based methods, for example, the Bayesian optimization, genetic algorithms, they have been used to address this problem. These methods actually are data efficient because they don't need any data for training, but they are limited in optimality due to the non-convexity of this problem. And they are also constrained to small scale circuits with a few device parameters. Supervised learning is also applied to address this problem by training a neural network model, which can predict the device parameters by using design specifications as input. Yet, this method achieves low design accuracy because usually the number of outputs here, the device parameters, can significantly exceed the number of inputs if we are using supervised learning to address this problem. Usually, we can not achieve a high accuracy. In addition to this one, supervised learning also needs a lot of data for training. Reinforcement learning is the most recent method that have been used to address this problem, often acknowledged by the community to achieve the state-of-the-art performance. In reinforcement learning settings, an agent lists an optimal policy to take actions in an environment that can maximize the return or reward based on the status. In reinforcement learning based inverse design, the actions here means we need to set the device parameters. For example, increasing the device parameters or decreasing the device parameters. The environment here, basically, it is kind of like a circuit simulation environment, which is used to extract the performance or reward for this design. The reward basically it describes how current or intermediate design is close to the design goals. And the status can be the intermediate design of these analog circuits. Reinforcement learning methods can achieve high design success rate, address more complex analog design with tens, 20s, more than 20s device parameters. And they can also find multiple trajectories towards the desired design parameters. Therefore, they can better address this one-to-many mapping problem, the non-convex optimization problem. This slide just to show you a quick deployment example of a reinforcement learning engine if it is well trained. So basically, when we use this reinforcement learning engine to find the device parameters for a given design goals, this reinforcement learning engine will start from this initial points and then move progressively towards the final design goal. And here, this quick note is that for this power consumption, this design specifications are actually, the smaller this value is, the better performance it is. However, reinforcement learning methods still require extensive data for online learning. And the training process of this reinforcement learning engine can take much longer time than supervised learning because we needed to use these time-consuming circuit simulators to obtain the reward from for the training loop. And during the practical analog circuit design, depends on the complexity of circuits and the complexity of simulation method that you are using. Each round of simulation can vary from like minutes to hours. Imagine if you want to train this reinforcement learning engine with like 100K interactions with this environment. The training time should be very, very long. So to address this challenge, we propose a sampling efficient strategy by combining with other optimization methods. Specifically, we combine reinforcement learning with Bayesian optimization. The key idea is that we can use Bayesian optimization to find a suboptimal or pre-optimized point for reinforcement learning engine. And then reinforcement learning engine can be applied for fine-grained search. This strategy, hybrid strategy, can reduce both training cost and deployment cost by reducing the searching trajectory length. But we think, although these hybrid strategies are very effective, but it's a little bit more complex as it involves various optimization methods and learning methods. Another method recently proposed by the community is to develop a surrogate model to replace this physical circuit simulation environment. Instead of using time-consuming circuit simulators to obtain the rewards, or to obtain the circuit specifications, a trained neural network model can be used for efficient predictions of circuit performance. So basically, we train this model to replace the environment. So this can significantly short the time that we used to acquire rewards, and it can significantly improve the training efficiency of reinforcement learning engine. But surrogate models still require extensive data for training. So in a summary, from the perspective of design effectiveness, reinforcement learning can achieve the best performance. However, it needs lots of data for training, either by training a reinforcement learning engine itself or training a surrogate model. So here we ask a question, can we pinpoint AI-driven methods that can have advantages of reinforcement learning, but with improved data efficiency and even can bring new merits for for AI-driven analog design automation? The answer is yes. So recently, we have successfully applied generative AI, basically a diffusion model, to address this problem. With diffusion model or the broad generative AI technique, we can reformulate the inverse design, conventionally an optimization problem, as a generation problem. So conceptually, we think this is feasible because we can train a model to produce high quality device parameters by using the guidance from the given circuit design specifications. And this generative AI method can indeed achieve better or high data efficiency than reinforcement learning, as we will show in the next few slides. But more importantly, we think generative AI has unique advantages that reinforcement learning methods do not have. For example, it can be directly used for synthetic data generation. This can enable lots of usage. For example, we can use synthetic data generation to train the surrogate models instead of using time-consuming simulators. And we can also open source synthetic data for reproducible research because we cannot open source the real data obtained from commercial semiconductor technologies. Yet, to make this method come true, we have to address several challenges. The first challenge is conditional generation. We try to use given circuit specifications as conditions to produce high quality. Any questions? Okay, I continue. So we basically try to use given circuit specifications as conditions to produce high quality device parameters. So this conventional diffusion process does not work well because a typical diffusion process generates new image data from pure noise. Therefore, we think this conditional generator is an ideal method to address this challenge by using design specifications as conditions plus noise. We can generate the device parameters. The second challenge is data modality. There are a lot of models on image generation, but our circuit data structure is actually in this tabular format. So we have the first column, this device parameters, the second column, the corresponding circuit specifications, which means that we cannot directly borrow existing generative AI methods for image or video generation. So to address these challenges, we develop a domain-specific conditional denoising diffusion probabilistic model. The short name is CDDPM for the analog inverse design by using these tabular data formats. The framework overview is shown here. The key idea is that basically for the forward pass here, we follow the same process of typical diffusion process. We add noise to the device vectors step by step until it becomes fully noisy. But during the denoising pass or the reverse pass, we embed the specification vector here and the diffusion time steps into this denoiser. Denoiser is the backbone of this CDDPM to predict the added noise. And in this way, after the model is trained, we envision it can generate optimal device parameters for the given circuit specifications. And if this method works, we also expect it can be used for synthetic data generator, which can be used for several downstream tasks, as I briefly mentioned a few slides ago. So with these key ideas, we develop a CDDPM and perform thorough evaluations on it to evaluate the performance. We choose two typical analog circuits as benchmarking circuits. One is operational amplifier, and the other one is LDO. LDO means low dropout voltage regulator. And we train 3 denoiser architectures like MLP, residue network with residue connections, and the transformer. And we also compare its performance to two baselines. One is from conventional optimization methods, genetic algorithm, and the other one is from reinforcement learning method. We use a comprehensive metric to evaluate the performance of CDDPM. We basically provide 3 key metric. One is generation quality. The generation quality means if the generated device parameters after we do a simulation, the performance satisfies the given design goals. The second one is data efficiency and the design success rate. The final one is utility and privacy preservation of synthetic data generation. We first show results on the generation quality. So for this evaluation, basically we randomly select 10 groups of design goals and order it as this one, G1 to G group, G10 for each circuit. And for each this selected group, we perform 10 generations. And after we generated these device parameters, we also do circuit level simulations to extract their performance. So here, each bar represents the statistics or variation, all these 10 simulation results. And this black dot is the target, is the design goal that we want, that we assign to this generator. So here we can see that the circuit performance simulated by using the generated device parameters are very close to these design goals. They can cover these design goals. So which means that if we use this generator, actually we can achieve a high generation quality. And we then compare the data efficiency and the design success rate between our method, CDDPM, and the baselines, including this genetic algorithm and reinforcement learning. So we can see that CDDPM can achieve high design success rate than GA and achieve a similar design success rate as reinforcement learning. But it achieves much higher data efficiency during the training process. To evaluate the utility of synthetic data, we basically use the synthetic data to train a surrogate model. So here, we do a lot of comparisons here. The basic difference is, I can elaborate a little bit here. So for this real-to-real means that we train the surrogate model by using real data sets that obtained from practical circuit simulator. And we also test the performance of this surrogate model by using real data. And for this since EXPB, this prefix Basically, we train the model by using synthetic data, but we test the model by using real data. So here we can see that the synthetic data, if they are used for training a surrogate model, they can also achieve high quality compared to the real data-based model. This is the true ground. This is the ground truth. And the conclusion is that we can see a transformer-based denoiser when they are used, when it is used for synthetic data generation, the data quality is the highest one. And this multiplies with 10 means we generate data with a size that is 10 times than the ground truth. So this comparison also shows that if we increase the data set for training, and we can further improve the performance of surrogate model. And finally, we show the evaluation results of privacy preserving. Basically, we use two typical metric from some like machine learning papers. One is this what's the staying distance, WD. The other one is this distance to closest record, DCR. Basically, we don't need to go into the details of these two metrics, but conceptually, if this WD value is smaller, which means we have a better preserving in utility. And for this DCR, if the value is smaller, which means there is a high risk in privacy leakage. So from this result, we can see that the synthetic data generation can preserve the privacy well, and meanwhile can maintain the utility. In summary, the key take-home message for this generative AI analog inverse design is that generative AI can not only offer a high design success rate, more efficient inverse design than reinforcement learning, but also can generate high fidelity synthetic data that can be used for downstream tasks that are unachievable by using other machine learning methods and the conventional optimization methods. All right. I just presented the first part. Now let's step into the second one, generative AI for topology discovery. And first of all, again, let's revisit the problem definition. So topology discovery is one of the most creative problem in analog circuit design automation. To design a circuit topology, human experts, they are required to determine the device types, like NMOS transistor, PMOS transistor, capacitor, resistor, inductor for use, and they needed to figure out how many devices to use. And finally, determine how those devices are interconnected with each other to achieve something useful. Something useful means we really can achieve some functional circuits. For example, operational amplifier, voltage controlled oscillator. And by the way, so the topologies of analog circuits primarily determine the performance, functionality, and efficiency of a circuit once a semiconductor process is finalized to implement them. This is akin to protein structure, right? That dictates the generation of amino acids. Conventionally, analog circuit topology design heavily relies on the expert domain knowledges. And to date, all analog circuit topologies that we can see from scientific papers or those, conceptual level diagram from industry products, they are all designed by human designers. This is because there is a significant lack of effective representations to abstract analog circuit topologies, such that we can leverage some methods like learning methods or other design techniques to automate the topology generation or topology discovery. Until recently, the breakthroughs in generative AI offer exciting opportunities to address this challenge by formulating topology design problem as a kind of generation problem. And the current explorations primarily fall into two categories. One is text-based generation using SPICE netlist to generate circuit topologies. And the other one is to use graph generation to generate circuit topologies. So I will introduce a little bit background here. What is kind of like a SPICE netlist? So text generations formulates the topology design task as a kind of like a code generation problem by generating netlist. So a SPICE netlist is a kind of like text representation of a circuit, which is widely used by circuit simulator like ngSpice or Cadence Spectra. But we needed to follow the strict syntax rule in SPICE netlist. So here we just show a toy example of a SPICE netlist by using like two transistor circuit. So we can see that this is a SPICE netlist. We can see that each row here represent a single device, and the four columns here in this bracket actually correspond to the 4 pins of this transistor. So 4 pins means the gate pin G, drain pin drain, source pin S, and this fork terminal is B. So we must follow this order and exactly match the pin name with each other to make sure this device is correctly connected. Therefore, if we use this netlist generation method to discover circuit topology, adding new devices or adding new connections is equivalent to generating a complete sentence that describe the connections of current devices to the new added devices. As you may realize here, right, this method is easily to error because a single letter here, if it is mispredicted, right, the generated topology can be fully wrong. Graph representation use graph generation basically use graph representation of circuits to generate circuit topologies. So one method here is to use this device level graph where you can see here, like each device here is kind of like graph node, and the connections between devices is formulated as graph edge. So in this representation, adding new devices or connections to a circuit basically is equivalent to adding edges or nodes to this graph. However, these methods are proven to ambiguity. For example, each transistor here actually has 4 pins, right? If we treat a single device as a kind of like a single node, it is unclear which pins connects to another device if we use a whole device as a graph node. We also develop a graph-based generation method for topology discovery. Instead of modeling each device as a graph node, we model each sub-circuit in an analog circuit as a graph node. This can significantly increase the generation accuracy, but the drawback is we will lose like device level information, this detailed device level information, right? So this will reduce the chances to discover novel circuit topologies with device level innovations. To summarize, while there are a lot of existing methods show the promise of generative AI in addressing topology generation, they are fundamentally limited to accuracy, scalability, and novelty. So to address these fundamental limitations, we recently developed the first scalable analog circuit generator, Analog Genie. So this Analog Genie is a kind of generative engine for automatic discovery of analog circuit topologies. It can discover analog circuits with arbitrary types and arbitrary topologies. The key idea is quite simple. So basically, we also use graph representation here, but we sequentialize the graph representation of a circuit topology into a Eulerian circuit sequence. The Eulerian circuit sequence is it's kind of like sequence that we at least towards each edge for at least one time. So this is a very old concept, and it's also a very established concept. So building on this sequence, then generating a circuit topology, right, is basically equivalent to predict the next device or the next device pin to connect, which is quite similar to what today's large language model do. So here, we just use this quite simplified graph for representation. We actually provide a more accurate device pin level graph representation. So we will introduce that technique in the following slides. While this idea sounds great, we face several key challenges. The challenge one is that there is a lack of a comprehensive analog circuit topology dataset to train a capable model, this analog Gini model. So we develop a comprehensive analog circuit topology datasets with 11 types of analog circuits, more than 300, 3,000 unique topologies from textbooks and papers from IEEE Explore. And this figure here just shows kind of like distribution of these different types of circuits. And we also develop a data augmentation technique by permutating the traversal paths of Eulerian circuit passes. So basically, for a unique circuit topology, there could be multiple Eulerian circuit passes. So using this way, we can augment the circuit paths for this topology library by averagely like 80 times. And we will see in our evaluation part, with the help of this data augmentation technique, we can actually improve the training performance by reducing the overfitting phenomenon very significantly. The second challenge is a kind of there's a lack of precise representation of a circuit topology. We introduced this one a few slides ago. Conventionally, let's revisit the conventional device graph representation. So conventionally, we basically treat each device as a graph node. So here there is a non-unique mapping between device connections. So if we just use these connections between these two devices, there could be several options, right? So we propose this device pin level graph representation for each transistor. Here we use this 5-node graph to represent it. In this way, we can ensure the one-to-one mapping between circuit graph and the circuit topology. If we directly connect these two nodes, then we are pretty sure, right? We will connect the drain terminal of these two devices. With these techniques, we develop analog Gini model and perform extensive experiments to show its performance. We use a dataset that contains 3,350 distinct topologies, spanning 11 circuit types, together with the data augmentation techniques to build the training dataset. And the analog Gini model is a simple decoder-only transformer consisting of like 6 hidden layers and six attention heads with only 11.8 million parameters in total. It is much smaller than today's GBD model. And we choose 3 baselines: CKT GNN based on variational autoencoder, Lamagic. This CKT GNN was developed by me in my PhD study, and this Lamagic is from IBM. And this analog coder is a recent framework that use existing GBT model to generate circuit netlist. And the first 2 methods actually are based on graph representation. We compare our performance with these 3 baselines. And we also provide some useful evaluation metrics, including correctness. Correctness means we will check the issues such as floating gates, shorting gates, or shorting nodes in the generated circuit topologies. This is a kind of very common electrical issues in circuit. The second one is scalability. We will record the number of circuit types and the largest valid circuit generated by each model based on the number of devices. Novelty means we will compare the generated circuit topologies to the existing topologies in our dataset. We will compare them to see if these generated topologies are different from those training dataset. The final one is performance. We will evaluate the performance of generated circuits. We will performing device sizing. Basically, we will perform inverse design and use the figure of merit. Figure of merit actually considers all the major metrics as a comprehensive indicator to represent the circuit performance. So we will use this full figure of merit value for performance evaluation. So we first shoot the training performance to see if the data augmentation techniques can be used to improve the training performance. So here we list all the training curves here. Basically, originally we just used the original data set for training without any data augmentation, just use a single pass for each unique topology. And then we augment that data set by using multiple Eulerian circuit passes. And here we can see that the data augmentation can significantly improve the training performance by reducing this overfitting. And then we compare our methods with state-of-the-art methods like TKDGN, LaMagic, and the analog coder. The conclusion here is analog Gini just achieved a new SOTA performance by outperforming all these four major metrics compared to the previous methods. And recently, we also do a further investigation on this analog Gini model. Basically, we develop an improved model, analog Gini Lite, which is enhanced version. And this analog Gini Lite can be used for more efficient and scalable discovery of analog circuit topologies. The basic idea is also quite simple. So basically, we prune the redundant nodes and edges in the original device pin graph such that we can reduce the token use to represent the circuits or to reduce the token during the generation process. The second technique is we will harness the reusable sub-circuits in analog circuits. As you may know, analog circuits actually they are different at the entire topology level, but inside each of these topology, there are a lot of common reusable sub-circuits. So we also harness these reusable sub-circuits for pruning to further reduce the tokenization in our tokenization table. So by combining these two techniques, we can further improve the efficiency and the scalability of analog Gini model. And the final result is that analog Gini Lite achieved a new SOTA again, even outperforming the original analog Gini model, as we show here. The final key take-home message for this generative AI for topology discovery is that sequentializing the graph representation of sequentializing the accurate graph representation of a circuit topology can enable scalable generation of various analog circuit topologies. And then the full optimization of circuit representation by using domain knowledge. Reusable circuits, right, can further improve the efficiency and the scalability of circuit generation. All right, so basically, I have presented the applications of generative AI to address the schematic level design of analog ICs. while this is the end of the talk, I don't think this is the end of the, generative AI-driven analog circuit design automation. So look into the futures. We find lots of opportunities and challenges. As we can see here, basically right now we are focusing on this schematic level design, but we haven't extended the research to this, entire end-to-end synthesis flow, especially for this final physical layout design. And meanwhile, as you know, there's increasing research efforts. There are a lot of people engaging in this field by developing lots of methods, how to develop open source data sets and benchmark, infrastructure to this emerging AI-driven analog design automation is also quite a challenge and is also actually in urgent need. All right, so this is basically the presentation of today's talk. So thank you very much. If you have any questions, I will be very happy here to address some of them.
Thank you, Wei. So thank you so much. Wonderful talk. And actually, we already have some question in the chat box. Can you check that?
Yes, let me check. The question is, would there be any benefit to adding an unsupervised learning step to the pipeline in addition to the existing supervised learning? Yeah, so can you specify your question a little bit? So in which step, in which step of this pipeline we need to add this unsupervised learning? You mean this is the inverse design or, the topology discovery? I still, cannot exactly pinpoint the question here. Oh, okay. I think the analog Gini model, right, is actually an unsupervised learning model. It is not, you know, um, a supervised learning model. Basically, we follow the decoder only formal structure to do autoregressive training, right? Which means that the output of this model, ideally, we want to make sure the output exactly matches the inputs, right? So this is the kind of like key idea. It is kind of like unsupervised learning or self-supervised learning. This is for the pre-training part. If you check that paper, we also have a fine-tuning part. Basically, the pre-training part only learns the foundational, circuit connections between different topologies. But how to make sure we generate a high performance topology, right? In that part, we will do some, labeling efforts. Basically, we will pick up a small group of circuit topologies and do sizing and then label their performance by using some heuristic rule. For example, high performance, low performance, and media performance. And then we will do like IRHF fine tuning to generate, to specifically make the model to generate high performance circuit topologies. So that's the basic flow of this analog Gini model. In this slide, I only present the pre-training part. If you are interested in that work, in a detailed manner, you can look into that paper. We have maybe like 2 paragraphs to state. We have also include the consideration of fine-tuning part to discover performance-driven circuit topologies. Yeah, exactly as you mentioned here. Yeah, thank you very much.
Some other questions from the audience? You can either unmute yourself to speak out or input a question in the chat box. Okay. So actually, maybe I can first ask some questions. So William, I have one question about the representation you mentioned that in the topology discovery. So you said that we have like the text description, like the
Yeah,
coding style, like the what is the convention from the spice, and also the graph representation, right?
yeah.
And you also
Uh-huh.
you also work on that. So like you have some previous clear work that you use in the graph neural, right?
Yes.
Yeah. I think that for that work that is based on the graph representation, right? And also like so we know that for right now for the generative AI, we have like two kind of the mainstream paradigms, the transformer based, the autoregressive, that is more kind of suitable for dealing with the coding, right? And another
Mm,
is the diffusion model. That is what you use in your first work. And
yeah.
I was wondering, so for this, especially for this topology level generation to extract the meaningful uh topology information. So whether like the graph transformer is a potential tool that can help us to better extract those like kind of the semantic information there.
Yeah, I think that's actually a very interesting, area, and my students is also working on that one. So instead of using language model based, this kind of like decoder transformer, right? Why not we just try graph transformer to generate those circuit topologies, maybe in a one-shot manner? So that is actually I think a very challenging problem. We tried that one maybe a few months ago, but the question is that you see here, right? For some circuits, maybe small scale circuits with tens of uh, device parameters, that is doable. But when we generalize this method to a more complex analog circuits, like with maybe 40 device parameters, and even beyond that scale, we don't find the model can work very well. So we're still working on addressing some challenges here. But I think, yeah, graph-based transformer indeed can be used here to for this generation problem. Graph-based topology generation problem.
Because from my understanding, so from the perspective of the first principle, so I believe that for the analog circuit, or even for kind of the more general kind of the CMOS circuit, right? For the
Mm.
schematic level, so it seems that so using the language kind of the derived model is it's not kind of naturally fit for that.
Yes.
Right, so
Yeah.
that's my understanding because this is not a coding. You can represent it as a kind of the code, but essentially, so we need to consider about the physics here, right?
Yeah, you are right. You are right. So I think here, right, in original VAE based model, like variation autoencoder, right, we actually follow that physics connection, directly generate a circuit graph, not using any, text based representation. Even for this analog Gini model here, although, we claim this is kind of like Eulerian circuit path, but actually we use text to represent each of these token, right? And in the future, we think if we can directly train on real graph data modality, that can work very well because it directly captures the physical connections of
Yeah.
device pins. Yeah,
Yeah. So that is the reason why I'm thinking about the graph transformer or
yeah,
still the
yeah, yeah.
innovation of the new version of the GNN. So because I think
Mhm.
from our toolbox, the current uh generative AI method seems is not naturally fit for the graph data.
Exactly. exactly. Yeah, at the current stage, we try to leverage, or also based on text-based generation. I think that maybe fits for like Verilog code generation, right? Because that codes actually naturally in text representation. But for this exactly graph like topology style, yes, if we can use exactly graph-based generation, I think it can do better potentially than this text-based generation. Yeah.
Yeah, another thing I'm not pretty sure because you are the expert in the civil circuit design, so you are kind of fully aware of the knowledge of all the underlying mechanism of those spies. So we know spice is a kind of the wonderful invention that can
Mhm.
convert the kind of schematic stuffs to the code. So I was wondering whether there's some kind of lesson we can learn from the abstraction behind the spies and then to further to reverse it back to use those the kind of insight how the spies that to to extract those information.
Yeah.
Yeah. So that is kind of my very rough sort of because this is not my
Mhm.
research area, but this is what I thought from the again from the perspective of the first principle. Right. So this
Yeah.
is
Yeah.
kind of two different kind. You can view this kind of two different modality. One is kind of more text-based modality. One kind of more
Mhm.
kind of the graph-based, right? So spice do one
Yeah.
that from one directions, but now when we want to generate back again, to generate those stuffs, whether I think we can view that so the spice is kind of the I think it's kind of the latent space, right? So because the interface exposed to the designer or to the human beings should be the graph based, right? But for the
Mhm.
text based, I think it's
Mhm.
kind of the from my point of view, it's kind of the latent space. But right now, what those stuff
Yeah.
whether should it be done still in the latent space or should be explicitly done in the graph space. I'm not quite sure, but I think that since the spice already in the several decades ago already did very good connection between these two spaces. I think there's many kind of lessons, experience we can learn from there. So that is my very rough
Mhm.
thoughts.
Yeah, yeah, I can basically discuss these questions, right? So, actually, I'm until today, I'm not fully sure which one or which way is the best way that we can use for like analog circuit design automation. But from my understanding here is that sparse netlist underneath actually is also kind of like a sparse graph representation, right? So basically, I think a sparse netlist will be converted like into a graph adjacent matrix that can be used to extract
Yeah.
electric. Yeah, yeah. So this is one way. I mean, from this semantic, definition, the sparse netlist actually capture the physical connections of device parameters. But
Yeah.
the key question is that for existing GPT model, even if they generate some text, general text, right, we can basically understand the key meaning of that sentences, even if some like keywords, becomes different, right? But for sparse netlist generation, we need to make sure, it exactly follow the syntax. In that way, we can fully say, okay, this text-based generation is reliable, for analog design automation. If we cannot address that issue in text-based generation, there's a gap how we can leverage, text-based generation for more reliable, practical analog design automation. Yeah.
Yeah. We need some kind of guardrail there. Yeah.
Yeah, yeah. That's the reason why we use graph-based because graph, as you mentioned, right, is kind of like explicit way to capture the connections of these physical devices. Yeah.
Okay. And
Mm.
another question is about the data. So we know that so data is pretty important for the generative model.
Yes.
So,
Mhm.
so can you elaborate a bit more, give us some more insights and information? So right now, what is kind of the progress in this area? So like how about the attitude from the industry? So whether based on academics' own efforts, so the data is already kind of the sufficient, or we need kind of more inputs from industry to kind of release more design files and so on, this
Mhm.
experience. We know that analog design is highly depends on the designer's
Okay.
experience, the seniority.
Yeah. Yes, exactly. Yeah, so you pinpoint the exact bottleneck in today's AI-driven research. Data set is still limited now, no matter from industry or academia. I think the key question is that maybe we have sufficient data set if we use either simulator to generate or we spend a lot of time, collecting these topologies from open source like papers, right? We can collect this data set, but how can we unify the data sets from different researchers or industries? That is kind of a key question. Yeah, those
Yeah.
data sets just distributed locally, not globally, right? Because there are a lot of IP confidential privacy issues. Yeah, so I think that's also a kind of like challenge, right? And in the domain, I think several different research groups of already open source partial uh, data set. That is not very comprehensive, but it's really useful now. At least we have some standard data set for use instead of building these data sets from scratch. For topology data sets, we already have. For netlist beta, sparse netlist beta data sets, we also have. And in digital domain, I think maybe the data set is much
Yeah.
larger. Yeah,
Yeah. Yeah.
yeah.
Variable styles. Yeah.
Yeah, very like style. But yeah, if we towards train a model like foundation model, yeah, I think data is still limited. So how can we unify those data to train a really powerful model? Yeah, that is also a key research problem. Yeah.
Any other question for audience? Because I have one last question. Yeah. Okay. If nobody asks questions, I will. So one last question is still related to data. Actually, that is already kind of not so confused, but still I already thought about for a while. So for a kind of VSI design, hardware design, I'm thinking whether do we really need so many data? So if we kind of imagine, so when we was a PhD student, right, we do not
Mhm.
kind of to need to kind of to observe so many data, but we can just like to learn from few kind of the very classical papers or designs, and then we can learn the insight. We can learn the key design strategies and the lessons and knowledge, and then we can begin to do the research, build the circuits, and so on. So, yeah. So I was running so specific to the circuit design or the IC design. So whether some kind of more efficient, data efficient way, we don't need to collect so much data. So actually already, so we even use the data that is inherited from the previous groups. That's many cases, that is how we train the PhD students, right?
Yeah.
Yeah.
Mm.
So
Mm.
so that's already kind of the confused me for a while. So I would like to listen to for your input since you're working on this.
Yeah, this is also kind of long-term vision I'm driving, right? Because I think the data is actually the bottleneck. So maybe we can explore some other, data-less, learning techniques or using like physics governed rules or policies for training. So basically, maybe we don't need to explicitly extract real circuit simulation data, but we try to learn those fundamental rules. Then based on that, we just need a little bit, data for generalization. But that is kind of a very, very challenging problem. Then even, challenging than the development of data set in the benchmarking infrastructure. Yeah.
Yeah. How to
Yeah.
determine those rules, how to give kind of, it's kind of the meta representation, in my
Yeah.
opinion.
You are right. I think there maybe now is there's a trend if we can really develop a foundation model. Yeah, I mean this foundation model maybe uh pre-trained by using a lot of data, but for each individual user, we just need a little bit of data for downstream task. Basically, this leverages the transfer learning technique, right? Yeah, but we will see. I think this domain is just emerging and exploding. I hope, hopefully, maybe in the next few years there may be more, innovative techniques that we can leverage. Yeah.
Yeah, it's quite an exciting area. So there's many new
Yeah,
things
yeah,
come up
yeah,
over the
yeah.
horizon there. Yeah.
Yeah, exactly. And compared to digital IC, analog design automation, there are even no standards. So yeah, it's
Yeah,
it's just a lot of works. Yeah, with different evaluation metrics. But at the current stage, if you can justify very well, it's also feasible and appreciated by the domain. But I think ultimately maybe there's a kind of like convergence, right? People will, as the progress of this AI-driven research, maybe people will reach some kind of like agreement, and finally we will provide some standards to guide analog data automation driven by AI. Yeah.
Okay, sounds great. Okay.
Mhm.
Okay, so we don't thank you so much. It's a very good discussion. I think we can have more discussion offline. Yeah.
Yeah,
And
sure. Yeah, I'm
thank
very
you
happy.
again
Yeah.
for giving this wonderful talk. It's very dense and very informative. And I believe that so our students learn a lot from your wonderful talk. And also thank everyone to attend our this week efficient AI seminar talk because next week I will be on an international trip. So our next talk will be next week, Thursday. Okay. So see you 2 weeks later. Thank you, everyone. Have a
Yeah.
wonderful day.
Thank you, Professor Yuan. Bye bye. Have a great day.
You too.
Mhm.